to be here. So I want to start by talking about how one can use tropical geometry or discrete methods to get information about one curve, so one curve at a time. And so here's the setup. So we have the disk, so a small neighborhood of the origin and the complex line, and we have some family of curves that's degenerating. And we have some, so let's say the total space is X, and this should be regular and semi-stable. So smooth over the punctured disk, and the smooth general fiber will be X, and X bar is the special fiber, this nodal curve. And so to this, I'm going to associate a finite graph. So G, which is the dual graph, it'll have one vertex for each component of the special fiber and one edge for each node. So here we have 4 components in the special fiber that meet pairwise, and one pair meets at 2 points. So the dual graph looks like this. So we allow multiple edges. And the idea here from tropical geometry is to use G to extract information that we might be interested about on the smooth general fiber. So the types of questions we might ask would be, so for which R and D does X embed in PR with degree D, or you could just ask for maps of degree D to PR, and maybe we should ask for these to be non-degenerate. So we don't want the image to be contained in a hyperplane, or when we have an embedding, we might want to know what's the Hilbert function of the image. So how many hypersurfaces of degree D prime contain the image of X, okay, when these embeddings exist. So I think on the face, it's not necessarily obvious that these questions are approachable from this graph G, but they are, and so the whole yoga of answering questions like this from the data of the graph is what we're calling tropical Brill-Noether theory. So, naively, we're interested in understanding the embeddings, but the space of embeddings is not compact. So we compactify and we study the space GRD of X. So this is linear series of degree D and rank R on X, and up to a small fudge factor, this is non-degenerate maps of degree D from X to PR. And the fudge factor is that there might be base points. And so let me fix G to be the genus of the smooth general fiber. And there's a number that floats around in this whole story, which is rho of GRD, which is G minus R plus 1 times G minus D plus R. And this number is a naive dimension estimate for GRD of X, the dimension of GRD of X. Yeah. Okay, so the Brill-Noether theorem, so proved by Griffiths and Harris in 1980. So calling it Brill-Noether theorem, so it's stated in the 19th century. But so So this is describing the dimension of the space of linear series when x is general. So if x is general, then this dimension estimate is actually correct. So if x is general, then dimension is rho of GRD, and empty if rho is negative. And then once you know the dimension, you might want to know what's the local structure. So what do deformations of these linear series or deformations of embeddings look like? And that was answered just a couple years later by the Gieseker-Petri theorem. So again, sort of a 19th century statement proved in the late 20th century. So this is due to Gieseker in 1982. And so again, if x is general, then GRD of x is smooth. So the deformation theory is as nice as you could hope. So the essential difficulty in both cases is that we still don't know how to write down a sufficiently general curve. Here, write down would mean, say, give generators for the ideal of some embedding in projective space. So we don't know things like, does there exist a sufficiently general curve of any genus greater than 14 defined over the rational numbers? So these sorts of questions are out of reach by current methods. And so the original proofs are by degeneration methods. And there have been several subsequent proofs. So one is a systematization of degeneration methods. So you want to degenerate curves in linear series. And so this was done systematically by Eisenbud and Harris. And they proved, so they reproved these two theorems in simple, clean way and proved many more results about curves and their moduli using this systematic method. And I should mention also, so there's a proof that does not use degenerations, but instead uses moduli of vector bundles on K3 surfaces and generic vanishing. And so this is due to Lazarsfeld. And I should probably mention that, so there's lots of things that are special about curves on K3 surfaces. So we know by work of Voisin, Aperdu, and Farkas that Green's conjecture holds for all smooth curves on all K3 surfaces. And this result via K3 surfaces is a little more subtle in the sense that we can only look at K3 surfaces of Picard rank 1. And we can only look at those curves that live in the linear series of the generator for the Picard group. And even then, we still have to take a general element of that linear series because we apply this generic smoothness. So it's probably just as hard or harder to write down a K3 surface of Picard rank 1 with large degree so that the genus of the general member is larger than 14. So we don't know how to do that. If you could do that over Q, then you would get existence of this curve over Q, but you still wouldn't get the curve explicitly because you would need to know what sufficiently general meant. But probably that wouldn't. Well, OK. But writing down these K3 surfaces is hard. We know they exist in all genera by variation of Hot structure. OK, so where do these graphs come into play? So this is a result with Coles, Drysma, and Robeva from a couple years ago. And so here I should draw a picture. So the picture is a chain of loops, and there are G of them. and I want to mark a vertex at each end. And so then I can talk about, okay, so I have an L1 and an M1 and LG, MG. And so these are the lengths of the top and bottom edges. And so when I say lengths, I mean there are actually many more vertices on this graph. So I have some discrete graph with many, many vertices, and I think of each edge as having length 1, so I can talk about the length of the top and the bottom of each loop. And I'm imposing a genericity condition, which is that Li over Mi is not equal to A over B, where A and B are integers and less than or equal to 2G. So I want some sufficient genericity on these edge lengths, but we can be very specific about what that means. And now the statement is that if G is a chain of loops with generic edge lengths, so that genericity condition then the dimension of GRD of X is rho of GRD. Okay, and so again, empty if rho is negative. So here what we can do is we can control the linear series on the general fiber just by knowing what the dual graph of the special fiber is. And so I want to give you an idea of how the proof goes. And in order to put the structure of the proof in context, I should first recall briefly the structure of the proof for limit linear series. So let me start with just a little. So here this would be length 4. So I have a number of vertices, maybe many, many, many vertices.
Yeah, but that would be
Yes, I never said anything about stable. Right, so that's right. So these special fibers are going to be very much not stable. And so we're not, right, so limit linear series gives you a curve on the boundary of the Deligne-Mumford compactification, which is not in the closure of the Brill-Noether special locus or the Giesecke-Petri special locus. We're not doing that. So when you stabilize this curve, you get a point on the boundary of the Deligne-Mumford compactification that's in the closure of the hyperelliptic locus. So it's a different strategy, it's a different curve, it's a different degeneration. The whole method is just a bit different. And I want to explain what's going on underneath the surface. Okay, so some notation. So I want so x bar was the special fiber. I want x bar I to be the irreducible components of the special fiber. What else? So I want L to be a line bundle on X. And so my linear series is some subspace of dimension r plus 1 in the global sections. And so in the limit linear series setup, the fundamental assumption is that G is a tree. So, or if you prefer algebraic geometry language, it's x bar is compact type. So the Jacobian is compact, or the sum of the genera of the components of the special fiber is G. Okay. And what this condition gives you is a distinguished way of extending L to the total space of the family, one for each irreducible component. So there exists a unique Li such that the restriction to the general fiber is L, and the degree of Li on the jth component of the special fiber is d delta ij. So all of the degree is concentrated on the ith component, and since sections of line bundles of degree 0 are constant, all of the interesting information about sections on the general fiber is going to be captured on the ith component. And so this W that we have is going to lead to a collection of WIs which live in the global sections on the ith component of the ith distinguished extension. And so this is living in the product over all I of the GRD spaces for the xi's. And in this framework, so there's some compatibility condition that these GRDs have to satisfy, which is given in terms of vanishing sequences at the nodes. And now you do an induction on genus. So you want these xi's to have smaller genus than G. The sum of their genera is G, and you set up an induction. So what's happening in the tropical proof, it looks quite a bit different. So instead of assuming that the dual graph is a tree, we want to, so the sum of the genera of the components is G, we go to the opposite extreme, and we assume that all of the components have genus 0. So there's not so much interesting linear series on the components, but this is equivalent to the condition that the first Betti number of the graph is G. So this is the number of edges minus the number of vertices plus 1. And in this setting, so there may or may not exist Li so satisfying this condition, so that the degree of the restrictions to the components is d delta ij. And so this prevents us from building the data that we would use in limit linear series. But instead of seeing that as a bug, we want to see that as a feature and study the obstruction. So we can measure the obstruction to finding this Li, and the obstruction is the component group of the Néron model of the Jacobian. For the general fiber. And so this is the fancy word, but to use these discrete methods, the key fact is that that component group, so it's some finite abelian group, but it depends only on the graph G. So this is the co-kernel of the reduced combinatorial Laplacian of the graph G. So I should remind you what this combinatorial Laplacian is. And it really is a sort of discrete or non-Archimedean analog of Laplacians in complex geometry. But explicitly, so delta of G is the degree minus adjacency matrix. So its diagonal entries are the number of outgoing edges. And at the ijth off diagonal entry is minus the number of edges joining Vi to Vj. And so this has co-rank 1. The row and column sums are all 0. So the reduced Laplacian is obtained by fixing a base point, fixing a base vertex. So you can delete the last row and column. That's how it's usually phrased. And you could think of this matrix as an operator from z to the vertices to z to the vertices. And it's tempting to think of this now as an endomorphism of z to the vertices. And this is a fruitful point of view. So you could then study the eigenvalues in the spectral theory of the combinatorial Laplacian. And in complex geometry, there's the Li-Yau inequality, which bounds the gonality of a Riemann surface in terms of the spectral gap of its Laplacian. And So that was used by Berkovich to bound the gonality of modular curves. And there's a corresponding story here where the spectral gap of the combinatorial Laplacian does give a lower bound for the gonality of the general fiber X. But that's not the point of view that I'm pursuing here. And so I'm going to instead ask you not to think of this as an endomorphism, but to think of this as a map between two different spaces. So I want you to think of the domain as being meromorphic functions. And the idea here is that if you specify an integer value at each vertex, then there's a unique piecewise linear function with integer slope linear on each edge that takes those values at the vertices. And here, on the right, we have divisors. And so this map is taking a piecewise linear function to the sum of the incoming slopes at each vertex times that vertex as a formal linear combination of the vertices. And this map, in a very precise sense, is a non-Archimedean Poincare-Lalonde formula. So on Berkovich space, there's a DDC operator, and so Amaury Thuillet's thesis explains how to see this as a non-Archimedean Poincare-Lalonde. But you're also free to just think like a discrete mathematician and write down a naive theory of divisors. So these are formal linear combinations of the vertices. And we'll say that this is effective if all the coefficients are non-negative. The degree is the sum of the coefficients. And two divisors are equivalent if their difference is in the image of the combinatorial Laplacian. And so the image is all divisors of degree 0. Or all divisors in the image have degree 0, but not all divisors of degree 0 are in the image. And in order to start saying things about linear series on curves, we need an analog of the dimension of a complete linear series on a curve on these graphs. And the definition is actually quite clever and beautiful and wonderful. And so this is due to Baker and Noreen in 2007. And they say that R of D, so the analog of the rank of the complete linear series of the divisor D, so this is the largest integer R, such that D minus E is equivalent to an effective divisor for all effective E of degree R. So I know it takes a few times to parse the definition, so the first couple of times you see it, but you could actually make an analogous definition of rank of complete linear series on an algebraic curve, that if you have a divisor on a curve, it moves in a linear series of dimension 1 if and only if it sweeps out every point on the curve. And it moves in a linear series of dimension 2 if and only if it sweeps out any 2 points. And so there's an equivalent characterization of rank for divisors on algebraic curves. And this is the characterization that seems to work well on graphs. So there are other definitions of ranks of divisors on graphs, but this is the one that so far has all of the applications. And I should say, so there's sort of 5 or 6 different notions of ranks of divisors on graphs. They all satisfy specialization inequalities, so I'll state specialization in a moment. They all satisfy versions of Riemann-Roch. And only one of them is known to follow from Riemann-Roch for algebraic curves. And that's the one that's called algebraic rank. It's due to Caporazzo. It's defined as a min, max, min over curves, divisors, degree distributions. And great. So as I say, so there's several different versions, and some versions involve labeling the vertices by genus, and all of this story works in whatever generality you want. And for simplicity, I'm just going to talk about the case where all the irreducible components have genus 0, which is where the applications come from.
How does this compare with effectivity on that actual curve?
Okay, so this is a good question. So the fact, which is a special case of what I'm about to mention, is that effective divisors specialize to effective divisors. And in fact, conversely. So for effectivity, so a divisor on the graph is effective if and only if it's the specialization of an effective divisor on the curve. So I think every algebraic geometer, the first 3 or 4 or 7 or 10 times so I haven't gotten to Riemann Roch yet. So okay, I should say that later. But the properties of these divisor functions are very closely analogous to properties of ranks of divisors on curves. But the proofs are completely different, and we don't know a way to go back and forth between the two in general. Okay, so I should get on with it and state the specialization lemma. So this is also due to Baker one year later. So suppose we have some extension of our line bundle to the general fiber, and say AI is the degree of L restricted to the ith component of the special fiber, and D is the corresponding divisor on the graph whose coefficient on the ith vertex is the degree AI. And so the specialization lemma says that the rank of D is greater than or equal to the rank of L. So if you thought that there was some geometric category in which this graph was the special fiber of some family whose general fiber was X, and that this R of D was some dimension of some cohomology group, then it's behaving upper semi-continuously. But we don't have any category like that.
But if you take just the special fiber itself as a curve and look at the rank of that lemma on the special fiber,
yep,
that's not necessarily equal to R of D.
No. And there's a beautiful definition of rank that depends only on the graph, which is due to Caporazzo, which takes those dimensions and does a min, max, min. And it gets an invariant that satisfies the specialization lemma. So my student Yoav Len proved that those two definitions, so they both satisfy Riemann Roch, but Yoav Len showed that these two are mutually incomparable. So, okay, and this is the one that we can use to prove theorems. So if you can control the divisors of degree D and rank R on the graph, then you can control the divisors of degree D and rank R on the general fiber. In particular, if there are none on the graph, then there are none on the general fiber. And so to prove the theorem, what we do now is classify all divisors of degree D and rank R on G, and actually all G of that form. So there's some, you have to take care of ramified extensions of the discretely valued field. So this is enough to get you things like dimension, and if you want to go deeper and get towards properties like smoothness, like Gieseker-Petri, or deeper properties like the Hilbert function of the general curve and its general embedding, then we need to get deeper into what's happening on these graphs. And so the first step of deeper is the tropical Riemann-Roch theorem. So this is from the first paper where the definition appeared of rank by Baker and Noreen. And so here, in order to state a Riemann-Roch theorem, we need a canonical divisor, which actually came much earlier. So Kg is the sum over all vertices of the degree of the vertex minus 2 times the vertex. And so this goes back at least to Zhang in 93. So, and there it showed up in an Arakhelov theory context. And so with that, and you can do a neat little computation and see that the degree of kg is 2g minus 2. And so now the Riemann-Roch theorem says what you would expect it to, that the rank of D minus the rank of K minus D is the degree of D plus 1 minus G. So same Riemann-Roch statement, but so as I was starting to say earlier, we have no way of deducing this from Riemann-Roch for algebraic curves, and we don't know of any one Riemann-Roch theorem that implies both of them. So using this Riemann-Roch theorem, what David Jensen and I showed so last year, and so now we modify the graph just slightly by introducing bridges, which doesn't change the classification of divisors of degree D and rank R. So this graph is just as good for proving Brill-Noether. But we need the bridges in order to prove the following. So suppose G is a chain of loops with bridges and generic edge lengths. So then GRD of X is smooth. So here we have a way of producing curves that are sufficiently general for Giesecke or Petri. And now we really do start using more of this non-Archimedean analytic machinery as well as this tropical Riemann-Roch theorem. So it really is, in some sense, a more sophisticated argument. So we take the geometric realization of the graph and realize that as a skeleton inside the analytification of the general fiber with respect to the discrete valuation coming from the punctured disk. And it's exactly the same. So we, again, have Li and Mi, and it's exactly the same combinatorial condition. The bridges have any length, but non-zero. Yeah. OK. And so here we really need to use the full strength of Poincare-Lalonde, which says things about reductions of rational functions and vanishing at points on the special fiber. And we have a patching lemma, which it seems one could think of this as some sort of plurisubharmonic construction, that we build piecewise linear functions piecewise, one loop at a time, and then patch them together. So there's a bunch of min constructions and patching constructions that happen here. And then we have a lemma on shapes of canonical divisors. So a canonical divisor has 2g minus 2 points. And what this lemma says very roughly is that it cannot have 1 point on every loop. So it has 2g minus 2 points. There's g loops, but there has to be one loop that's empty. And so the contradiction that we obtain in this argument after going through Poincare-Lalonde patching lemma is that we get a divisor that has 1 point on every loop. And that contradicts Riemann-Roch. So yeah. It's really a different flavor from the limit linear series arguments.
But you're saying something like if it wasn't smooth, then there would be a non-zero section of some structure.
Great. So we're using the same characterization of smoothness that Gieseker used, which is that the dimension of the Zariski tangent space at a linear series is rho of GRD plus the dimension of the kernel of the adjoint multiplication map. So W tensored with sections of K minus L to sections of K. And so that's why K is playing this huge role. So we're looking at all the piecewise linear functions that could come from sections of L, sections of K, and putting them together. So we've continued in this direction, and so what we've proved now and will appear soon, so could be summarized as the maximal rank conjecture for quadrics. And so what we're doing now is we're controlling the dimension of the space of quadrics that contain the image of the general curve in its general embedding of degree D and PR. And so G is as above with an additional condition on edge lengths, which I'm not going to state. But what I can say is that it's more subtle. So instead of just having a condition on the lengths that involves the top and the bottom of each loop, we have a condition that involves several loops that are adjacent to each other. And we are not going to allow there to be a small integer linear relation among those edge lengths. OK, and so then with this additional condition, we can say that for a general, and we can say specifically which general ones we're allowing. We just have to construct one. So for a general L and GRD of X, the multiplication map, so this is from sim2 of global sections to global sections of the second tensor power, has maximal rank. So it's injective or surjective. And so the conjecture, the maximal rank conjecture, which again is a 19th century statement, but this one is still open, says that if X is general and L is general, then mu n should have maximal rank for all n. And so we can do n equals 2. And there are other partial results on the maximal rank conjecture. So Balico and Elia, they proved maximal rank conjecture when R is less than or equal to 3. And in the non-special case. So those are the known partial results. OK, gosh. And I'm not going to get through as much as I hoped, but that's OK. So that's a sort of brief overview of how one uses one graph to get information about one curve. And so now I want to talk about what happens if you want to understand families of curves. What happens if you want to understand the moduli space of curves, and how can you use these similar graph theoretic methods to get information there. And to explain this, I should explain an idea that goes back more than 40 years. So the idea is boundary complexes. And so the earliest reference that I know is from Daniloff in the early 70s. And this was rediscovered and worked on by a number of people, including myself in the 2000s. And here's how it goes. So X is a smooth variety over the complex numbers. And so say it's d-dimensional. And then we can choose a compactification where the boundary is a divisor with simple normal crossings. So this boundary divisor is the complement of X. And from this, we build a dual complex, which is the analog of the graph that we associated to the special fiber. But this is now associated to the boundary divisor. And this, so it's a delta complex. So it has one vertex for each irreducible component of the boundary. So let's say these components are di, and one edge for each irreducible component of di intersect dj, and so on. So one two-dimensional face for each irreducible component of di intersect dj intersect dk, and the inclusions among these faces come from inclusions of these irreducible components. And the key basic theorem here is that the simple homotopy type of this dual complex, so we could choose many different compactifications, and their dual complexes will be different, but the homotopy type is independent of all choices. And there's two essentially different proofs of this fact. So, yes, okay, is an invariant of x. So the two proofs, one is by weak factorization of birational maps. And so this is the proof that gives this stronger fact, this simple homotopy type. And the other proof is by retractions to skeletons. So this is in the world of Berkovich spaces. And this gives homotopy type, but not simple homotopy type. And so I mention this because if we want to study moduli of curves, moduli of curves are smooth, but they're not varieties, they're stacks. And so we need to extend this story to Deligne-Mumford stacks. And it's relatively straightforward. So X is a smooth DM stack over the complex numbers. And so we can, so let's say we have, so there exist these simple normal crossing compactifications in this context as well. But here I shouldn't say simple normal crossing. I should say normal crossing compactification. So simple normal crossing compactifications do exist. But if we want to work with the Deligne-Mumford compactification of MGN, that's not simple normal crossing. So we want to really just be able to work étal locally. And so then we should be able to work with normal crossing compactifications. And the way it will work is we choose a cover, so V0 to X, where this is a smooth variety, and the preimage of the boundary is simple normal crossing. And so then we know how to build the dual complex for V0, and we build the usual diagram. So V1 is V0 crossover X V0. And so then we have the two projections from V1 to V0, which induce two maps from the dual complex of V1 to the dual complex of V0. And the dual complex of this X prime is defined as the topological colimit of this diagram. So if you have a global quotient, so if X prime is V0 mod some finite group G, then G acts on the dual complex delta V0, and this is the topological quotient of delta V0 by G. And now G might act by non-trivial, so some elements of G might act by non-trivial automorphisms on some of the faces of delta V0. So if you wanted to put a simplicial complex structure or delta complex structure on this, then you should first take the barycentric subdivision of delta V0 to get that cell complex structure. And I should say there's one sort of, you might be tempted to take this colimit in the category of topological stacks. And there's a problem, which is that that colimit is not independent of the choice of cover. So the topological colimit is independent of the choice of cover, and Dan Abramowitsch is working on a wonderful theory that lives in the world of non-Archimedean analytic Artin stacks that will explain what the stack structure should be on this boundary complex. Okay, so then the basic ideas are in the work of Thuillier, and the final details were carried out with Dan Abramowitsch and Lucia Caporazzo. So the homotopy type of this dual complex of the boundary depends only on the open variety. And the proof this time is, so we don't have a weak factorization theorem for Deligne-Mumford stacks, and so the proof goes through Berkovich spaces and non-Archimedean analytic geometry. So one of the basic theorems about these boundary complexes for varieties is that their reduced homology computes the top-graded piece of the weight filtration on the cohomology of the open variety X. And that goes through in this context as well. And there's something a little technical to check, but essentially nothing happens. And so the statement here is that the 2D graded piece of the weight filtration on H, 2D minus I of the open stack X with Q coefficients is canonically identified with the I minus first reduced homology group of the dual complex of the boundary. So what this means is that when so this piece of the weight filtration is essentially combinatorial. And so the reason for going through all of this, so like I say, nothing much happens in these arguments, but we want to study specific examples. And the example we had in mind to start was to take the moduli stack of curves and X prime to be the Deligne-Mumford compactification. And what's true in this context, and what seems to be true in many related contexts, is that when you have a nice modular compactification, then the dual complex of the boundary has a modular interpretation as well in some piecewise linear world. So the theorem, so this is with Abramowitsch and Caporazzo. And so the theorem says that if we take the dual complex of the boundary of the Deligne-Mumford compactification, then this is naturally homeomorphic to a moduli space of stable tropical curves. So this is so let me just draw a picture. So essentially what this is these are dual graphs of singular curves in the boundary of MGN bar. So in genus 2, it could look like this, but we assign edge lengths to each of the edges. And so one of the loops could shrink, and this is a compact space. So in the limit, when some loop shrinks, we label the vertex by the number of loops that have shrunk down, and so this is a dual graph labeled by the genus of the components, and then we might add markings. And these markings you could think of as being half edges. Okay, and so if you just look at graphs with first Betti number g, and I should say something that the sum of the lengths, so we normalize so that the sum of the lengths of the bounded edges is always 1. So you could think of these legs as being unbounded edges. So these moduli spaces of metric graphs with the sum of the edge lengths being 1, if you require that the first Betti number is actually g, then you get this color-Voigtman outer space. So, okay, so maybe, from faces I see that I need to say more. So this is a compactification of x, well, okay, so mg tropical is a compactification of xg mod outer automorphisms of fg. So outer space is a specific realization of the classifying space of the outer automorphism group of a free group. And what we're doing is, and it has a modular interpretation as a moduli space of metric graphs with first Betti number g. And we're compactifying that in a way that's analogous to the way Deligne-Mumford compactification compactifies the classifying space of the mapping class group by letting these loops shrink down to points and labeling them by genus. What's that? xg is, so this is outer space. So this is a moduli space of marked, labeled metric graphs with first Betti number g. So it's the analog of Teichmuller space. It's contractible. So it's a contractible space with a nice action of the outer automorphism group of fg. Okay. There's so much more that I would like to say, but I need to end soon. So what this allows us to do is, so if we want to compute invariance of MGN that can be extracted from the dual complex of the boundary, we can now use the modular interpretation of this boundary complex to aid in those computations. And so that's what I've been doing in joint work with Melody Chan and Soren Galatius. So we have a specific subcomplex, which we call the repeated marking locus. So this is in the tropical moduli space. And what we can show is that that subcomplex is contractible. So we have this large contractible subcomplex, and so now we can start computing invariance of MGN trop by contracting that locus. And so we get full information when G is 1. So a corollary is that, so the boundary complex of the Deligne-Mumford compactification of M1n is homotopy equivalent to a wedge of n minus 1 factorial over 2 spheres of dimension n minus 1. So from this, we get what the top weight cohomology of M1n is, that it has rank n minus 1 factorial over 2. So this is for n at least 3, and it's contractible when n is less than or equal to 2. So we get this large vector space in the top weight part of Hn of M1n. And if we keep track of things more carefully, we can even get that cohomology group as an Sn representation. And we find that the 2nth graded piece of the weight filtration on HK M1n Q. So the non-trivial group is the induced representation from the dihedral group to the symmetric group of the restriction from the symmetric group to the dihedral group of the sign representation. So this is when k is equal to n, and it's 0 otherwise. So we can actually get sort of interesting computations about the moduli space from this moduli space of graphs. And maybe since time is short, I should stop here.